What's up? Okay, so today we are going to be talking about computational complexity. In theoretical computer science, there's a very big question, probably the biggest question ever to exist in theoretical computer science. And this question is P equals NP? I'd like to start off with P equals NP. Okay, think of it like this: termites are ants, okay, but are all ants termites? That's basically P equals NP. I know that sounds very weird, but let's look at it. First of all, we'll start off by knowing what an algorithm is. It's a step by step instruction on telling your computer how to perform a specific task. Every algorithm has a time complexity. That's basically how well the algorithm scales or how efficient the algorithm is. If you are into computer science or you are pursuing a computer science degree in the university, you'll be familiar with the big O. This is basically the efficiency of the algorithm in the worst case scenario. The big O is represented in this right here. Um, I would have liked to illustrate all this on a paper, but I currently do not have a camera to show you my book over here with all my illustrations on it. So please bear with me. I'll put up all the illustrations on the screen so you can see it. The N in the formula for the big O is basically the number of inputs in the algorithm or the number of inputs you give in the program. The F is basically the number of steps in the function for the algorithm and how the steps will increase as the number of inputs increases, which is n. Back to P equals NP. Let's take a set of problems in the P compound of P equals NP. The first one I'd like to talk about is the linear search. This is basically taking a list full of items and comparing it to an item in the list to check if it's available in the list or not. If you don't understand what I'm saying, what I'm basically saying is we have a list of 5 items. Let's say an apple, orange, banana, milk, and nuts. Okay, let's take the worst case scenario where the item we are looking for is the nuts, and nuts is at the last position in our list. The algorithm will take n number of steps where n is equal to the number of inputs or the number of items in our list. Okay, so the algorithm will take n number of steps to finally um, confirm the selection of the item and then the item you are looking for in the list, if that makes sense enough to you. So basically, n items is equal to n steps the program will take. Our big O would therefore be O into bracket n, which is a polynomial function stating that our algorithm will take n number of steps to, to complete the algorithm. The second type of P class problem I'd like to introduce you to is the insertion search. So this basically is just a list of values arranged in an indefinite form. And the insertion search will basically go to each value one at a time and replace it to its correct position. So if you have a scrambled list of numbers, the insertion search will basically go to each number one by one and put it in its right place. Let's have the worst case scenario, which is the big O. In the scenario where our n is at the last place and is supposed to be at the first, it will take n amount of steps to sort our to fix our nth value back into its original position. Mathematically, this is n times n. Our big O will be n times n, which is n squared. We have to note that n squared is also a polynomial function. As of now, the question P equals NP in theoretical computer science still remains in a land of mystery. Mathematicians and computer scientists have been trying to come up with a solution for this, or for they are trying to come up with a proof for this, but to no avail, at least for now. And this question in computer science is so important that the Clay Institute of Mathematics offer $1 million for the person who is able to prove if P is equal to NP or if P is not equal to NP, and that is not done yet. So Now that we've defined what our P class is in the P equals NP problem, let's look at our NP. NP is basically the non-polynomial deterministic class. Okay, let's take some problems in the NP class. I'd like to start off with the traveling salesman problem. This is basically the most common NP problem, especially in the field of computational complexity in computer science. So basically what the problem says is that given an n amount of cities, is there a path connecting all the cities in the shortest route which is equal to or shorter than the length L given? Okay, let's try and illustrate this. If I'm giving n to be 4, which is 4 cities, okay, in an illustration of 4 cities, there will be 3 different routes given in 4 cities. There will be 3 routes I'll use to take around those 4 cities. There are 3 different route combinations. Given cities to be 5, given n to be 5, my route taken will be 12. Now check this out. If the cities were to be 30, okay, the root combinations that will be left will be 4.42 quadrillion roots. I don't think we have any computational power to compute 4.42 quadrillion roots in any amount of time right now. Now check this out. If we had a supercomputer which had the ability to even compute 10 million roots in a second, we'll still need this amount of years to be able to complete this algorithm. That's impossible. If you don't know how large this amount is, then let me give you an insight. Okay, the universe is this years old, and this is the amount of years it will take to compute that. Imagine how long that is. Now you might ask, why is the scaling for an NP problem so bad and so inefficient? Especially in a problem like this, the traveling salesman. The big O, or the formula for n in the traveling salesman, is n minus 1 factorial all over 2. This is basically saying n, the number of steps, which is n, increase factorially, okay, which is making a big O n factorial. Okay, this characteristic of NP class problems of poor scalability is what makes it non-polynomial deterministic. It will only be polynomial deterministic, or it's only running polynomial time if we are able to check all the possible routes of the cities simultaneously, which is practically impossible right now. So yeah, there are currently theories on what computers cannot do, at least now, as in terms of efficiency, which of one being the P equals NP, which I just explained to you. The second one will be factoring numbers. Let's take the encryption system for now, like the RSA encryption. Okay, what it basically does is it takes a very, very huge prime factor, sorry, two prime factors, very huge ones, multiplying them to get a huger product, okay, and then they use the factors as the secret keys, okay, and it's be impossible to decrypt an RSA encryption because no computer can factor huge numbers of a product like that. If I was given a number, let's say 20, a classical computer can compute the factors of 20. I can compute the factors of 20 by saying 2 and 10, because I know 2 and 10 multiplied will get 20. But given huge numbers like this, it will be impossible to factor. So factoring huge prime factors is one problem classified under NP and said to be impossible for computers to solve, at least as of now. Not not to tell of when quantum computers are available to easily do this job. So as of now, we have no computers that can do this efficiently right now. Now, what if P is indeed equal to NP? This would be very, very good news for mathematicians and very bad news for cybersecurity agents because cryptography will literally come to an end. Someone will be able to tell your password as easily as you were able to create your password, or someone will be able to decrypt a password as easy as the computer was able to encrypt it. That would be very bad news for cryptography as we know of it now. And that would be good news for mathematicians. That means for every NP classified problem, there will be a relatively easy polynomial time solution for it. So for how easily they will be able to check if some proofs are correct, they will be equally easy for them to generate the proof for the problem or to solve for the problem or calculate for the problem. That would be very good news for mathematicians. So we can safely say NP will only be polynomially determinant or P will only be equal to NP if we can check all the indefinite amount of possibilities simultaneously. That will require great computation power like quantum computers, which we currently don't have any access to right now. So yes, your encryption is safe, cryptography is safe, at least for now. I actually have a video that will be coming out on the dangers of cryptography, as of which quantum computers approaching the technology field right now. If you like this video, please subscribe and like. You can share to your friends who are interested in computer science or anything related to computers, programming, because a lot of programming videos, tutorials, and explanations like this will be coming very soon. And leave your comments. Bye bye.